I don't remember.
All right.
Yes, I think so.
The first project I did was I made
I don't know. Okay, I'll definitely remember that. It's a physics.
yeah, I guess we're about ready to go.
Yeah.
So guys, we're about to start the talk. This is Don Dini, and the talk's, as you can see, on machine learning and big data architecture. So I'll let you speak for yourself.
Thank you very much. Hi everybody, my name is Don Dini. Thanks very much, Brian. So just a bit about myself. So I graduated from here. I got a master's in computer science in 2005. Graduated, went on to do various interesting things. Today, including I was a lecturer here in computer science for a short while, in which I taught a class on web frameworks and building web services. I went out just like 6 months ago up to Silicon Valley, work at a company called NAC, where I'm the chief data architect, and I work on basically big data systems and applying machine learning in production and commercial environments. I also started a company called Method in Mind, which has undergone various iterations, but what we're doing is we take artificial intelligence inspired mobile software. Although our website needs to be updated. But anyway, so what I'm going to do today, please feel free to stop me with questions at any time. So I want to talk a bit about, first of all, what is this big data business? Why is it a big deal? What are people doing today? So not research systems, but like what is deployed, what are people doing in some sort of commercial capacity? Approaches to building these systems. So we'll use a simple but non-trivial example and think about how to build these systems. And then a Q&A about anything that I talked about here or anything that you would like. So what are we trying to do? So it's actually an old problem. So there are commercial problems like that people have been trying to solve since forever. Things like who are my customers? What do they want to buy? How do I persuade them to buy what I'm selling them? Or more generally, just trying to predict or gain some sort of insight into a phenomenon. So things like disease or rental prices. So things like, for example, if you're looking at so this is actually a real problem that people apply machine learning techniques to solve, is if you look at the housing market, you look at how much are houses selling for, and like what are things that might influence that, things like square footage, where it's located, what year it is, who the president is, all sorts of pretty things that you might want to throw in there. And can you find some sort of correlation between that and how much homes sell for? And so like if you can sort of extrapolate that into a model, you can make predictions. You can sort of say like, well, I have this new home on the market, how much will it sell for? So here's a great example. Does anybody know what this is? Has anyone seen this before? So this is a map of cholera outbreaks. In England in the 1800s, there was a massive cholera outbreak. And people were just dying left and right, and nobody really knew what to do about it. They thought God was angry. And this gentleman called Jon Snow, not the Game of Thrones Jon Snow, he was a physician, I believe. He thought he was basically, it was amazing. It was basically one of the first applications of what we would call today a big data problem, which is basically, he looked at where people were dying of cholera, and he plotted it on a map. And like, that's all he did. He's like, I'm going to take just all of these records of like people having outbreaks and dying, and I'm going to put it on this map, and let's see what we can discover. And what he found out, and this was the map that he produced. So I believe all of the squares represent a death, and he discovered that they were centered. He looked at where they were centered around, and he went there and he saw what was there. What he discovered was a well, a water well, and he just had this hypothesis that if he went there and he broke off the spigot, making that well inaccessible, that would have an impact. So he did that. The map that he made, like, the following year had like no deaths on it. It was like dramatically, like he clearly found the cause. It was this well, and it was entirely due to visualizing it. So you have these, hey gentlemen. So you have these these old problems, both commercial and sort of generally you're trying to solve. Who are my customers? What do they want to buy? So how would you solve this? The first thing that you might do is just to try to solve the problem. Who are these people? What makes them tech? Does anybody know who this guy is, the man on the left? Has anyone seen him before? That is not surprising. His name is Edward Bernays. He is the nephew of Sigmund Freud. He's the creator of the modern advertising industry. So if any of you are ever find yourselves bored and you're trying to procrastinate, I highly recommend you go watch this documentary. It's one of the most thrilling documentaries in the universe. It's called The Century of the Self, made by a guy called Adam Curtis. And he talks about this guy and how he created the modern advertising industry. So what he did is he used his uncle's theories and psychotherapy in general to reason about human beings and about how to make them buy things, or to persuade them to buy things. So he came around in the 1920s, 1930s, and prior to him being there, what advertising looked like was purely functional. So what happened is people would go up to you and they would say, here are a pair of jeans. They're very rugged. They will fit you. You could buy them at a store that's nearby to you. You should go and buy them. Like, purely from functional perspective. And so what happened is, Edward Bernays came on the scene. He had all these ideas about psychotherapy. Cigarette companies came up to him and they said, half of our market, women, are not buying cigarettes. Please help us to solve this problem. How do we persuade them to buy cigarettes? So what he did is he staged this this massive event during this parade, in which he basically the effect was he associated cigarettes with the women's liberation movement, and he forever created this idea that where previously women, there was enormous social pressure to prevent women from smoking, they sort of, in dramatic fashion, he hired a whole bunch of women on this float to suddenly, in front of a bunch of photographers, pull out a carton of cigarettes from underneath their clothing and like light up a bunch of cigarettes sort of in brazen view of the camera. And from that moment forward, cigarettes have been associated with women, with women's liberation, to some degree even still today. But that completely changed everything. After then, products forever became associated with emotional appeal, and not purely functional point of view. Today, advertising looks like this. So this is, Amazon is looking at what you are buying, and they say, oh, you bought this history of things, here's what you should buy instead. So they are not reasoning at all about who you are. They're not talking to psychotherapists. They don't care. You are a black box. They're simply saying like, ah, here, you came to the site, you bought these things, you should look at these other things. So let's look at, here's what we showed you, here's what you ended up buying. And they examined the correlations between what they showed you, what you did, and other people like you, what they showed them, and what they did. And they created this product, the recommended for you thing, which today earns Amazon about 60% of their revenue, is the recommended for you pen, which is amazing. So instead of hiring a bunch of psychoanalysts, they did this correlation, sell things to people at a much larger scale, much more cheaply. Another example, Netflix. So you guys may remember a couple of years ago, 2008 at this stage, there was this prize that Netflix announced, which was they wanted people to increase the quality of the recommendations that they were giving. And they said, like, here's our data. Here's our data about what people chose, what people put in their queue. Please improve our recommendation results. There were tons and tons of teams out there. One of the teams that did the best was a psychologist who, again, is doing this overt reasoning about what people are like. And he had, like, really, really great performance. What ended up happening is, so I think Netflix ended up using some of that team's algorithms. Actually, I think he was eventually destroyed by a data-driven team. But what happened is Netflix's model, since this prize, switched to a streaming-based model. So now, like, they're like primarily a streaming-based site. And that algorithm got replaced by this. These two gentlemen, Sadiq Kahadia, Richard Rohr. they created a solution to this problem of co-clustering, which is, again, is one of these things which basically treats human beings as a black box. So on the inside, or on one side, it's just the person coming to the site, you're just showing them some things. On the other side, you watch what you're recording what they selected to play. And they're just creating this correlation between what you show them and what they end up doing. So I'm going to be talking in a little tiny bit more detail about co-clustering later on, but they implemented this, which for a long period of time was running in a laptop on Sadiq's desk in Netflix, and that was Netflix's recommendation algorithm. And it like dramatically increased the quality of their recommendations. I forget the percentage, but it's in like the 90% range, where it's like the quality of their recommendations dramatically increased. One last example, I want to show it to you because it delights me. Okay, chemists. So in the 70s, the EPA, Environmental Protection Agency, this is what they did. So of course, what they do is they're getting tons of chemicals every year. They're basically just trying to figure out, is this toxic? And they just do this all the time. We're trying to figure out if a chemical is toxic. In the 70s, what they did was you would give them a chemical. They would take a mass spectrograph, which basically is how much of what sort of thing is in this substance that I'm looking at. You would take this and you would give it to a chemist who is highly trained, super expensive, takes a lot of time, can't really crank out a lot of products in a period of time. But anyway, give it to him, and he would come to you and be like, yes, this is toxic, no, it is not toxic. So the EPA was like, this sucks. Can we replace these people with an algorithm? So they went to a bunch of data people, and they said, like, can you do this? We want to give you the mass spectrographs instead. Can you come up with an algorithm that from the mass spectrographs predicts whether or not these things are toxic? And the answer was yes. With 95% accuracy, they predicted toxicity, which was amazing. They used decision trees, which is an algorithmic approach to classification. So I'm trying to illustrate this basic trend. So previously, people thought long and hard about like what is the nature of the thing that I am trying to model, and like trying to produce predictions based upon that, and trying to think about persuasion and insight into a phenomenon based on creating an explicit model. Today, people are solving the same problem, but at much greater scale, much more cheaply, just using data and correlations. So what I want to talk about is how people are doing this. Okay, cool examples that are happening today, deployed systems. One, medicine. So this is a really interesting problem. I forget the name of the company. So what they did was they went to, okay, so if you were admitted to an emergency room, when you are discharged from the emergency room, some of those people have to be followed up. Some of them are sort of in greater need of care after they have left the emergency room, and some are not. And the goal is basically, but there are only so many resources to go around. So the hospital is trying to determine who should I call, who should I check up on, who continues to need our help. This company came on the scene and they said, okay, we're going to look at all of the records of people who were admitted to emergency rooms, and we want to just sort of observe who ended up requiring the most help. And what they determined is that if in the report written in the medical records, if it contained the word fluid, those people, that dramatically jacked up the probability that those people had to be followed up with. So like they would ask them, they were like, well, why is that true? Like, what does that have to do with anything? And they're like, we don't know, that's not our department. Like, we don't know. We have no causal explanation. We just observed that, like, if this word appears, it dramatically increased the probability that they needed to be followed up with. So that was really interesting. Okcupid. You don't actually have to go there and go date people, but they have this amazing blog. So it was founded by a bunch of statisticians. Everybody knows what Okcupid is. Does anybody not know what Okcupid is? No. So Okcupid is a dating site. So basically, it's you go there, you create a profile, and they have this sort of system by which they sort of recommend people to use. So like you go, you're looking at a profile, they'll be like, oh, do you dislike this person? Here are people who are like this person, but are different in some dimensions. So for example, this person is more adventurous, this person is more sloppy, this person is more conservative, and like sort of gave you, they're sort of pulling features out of these people. It was found, as I was saying, it was founded by a bunch of statisticians, and that's what really led to its amazing success. They published this blog in which periodically they talk about really bizarre insights that they get from their data. So what they're examining is things like, all right, let's look at features about people's profiles and how that influences whether or not they get a response when they message someone on the site. And they look at everything. They look at things like what kind of camera did you take a picture with? Like, was your picture black and white or not? And like, does that have an influence on people? So some of the things that they found were, if you are a male and you send a photo to a lady and you are not smiling in your photo, that increases the chance that you will get a response. Whereas if you are smiling, that decreases the chance. And like, you could posit explanations, like maybe it means like ladies tended to like the mysterious looking folks, and you know, God knows. But like, that's what they found. And they found that, like, for example, another thing which was amazing, which was people who have some sort of an unusual trait, for example, like a tattoo, like a facial tattoo, or some other kind of body modification, or I don't know, they like attach cords to their head or something like that, or whatever. Like they would try to normalize that out when they took photos of themselves. Like, you know, I look weird. I want to appear attractive to people, so I'm going to remove those things. What they found is that, okay, so most people on the site weren't looking for those things, but there was a small number of people who were explicitly after those weird traits. And if you didn't reveal that about yourself in this profile, they wouldn't find that about you. So what they discovered is, due to this analysis, they're like, okay, if you are weird, you need to just put that out there. You need to tell people that you are a weird human being, because that will enable these people who are looking for you to find you. And lastly, another cool example I want to talk about is NAC, which is my company. This is the company that I work at, which I'm the chief data architect. So what we do at NAC is basically, people play games that we create. We look at the data that is emitted from you playing games, and we learn things about your personality, in a nutshell. And this is used, so most of our clients use this from a HR perspective. So the idea is that you're a headhunter, and so for example, you could be like at a gigantic company, and who shall remain nameless. They came to us and they're like, here's an employee that we really like, or a group of employees that we really like. They're fantastic. We don't know what it is about them that's really great, but we want to find more people like this. Can you please help us? So we said, sure. So what we did is we had them play this series of games that we created. And these games were created, we hired people from the video game industry. So these are like top-notch people who are from the video game industry. They came to our company and are making games, and they work with psychologists and neuroscientists in order to figure out what sort of data should we be getting from games. And we sort of created this like personality profile from people who are playing it, of the people who are really good. And then what we can sort of do is you can say that, for example, when you have a new applicant, you can sort of say like, okay, here are people who are like the person you said was really good. So perhaps you should consider looking at these people. Yes, in a nutshell. Okay, so we've talked a little bit about what big data systems are, why they're important. So just to reiterate, it's same old problems, trying to persuade people, trying to figure out what people want to buy, trying to gain insight into problems. But by going into a data-driven approach instead of an explicit modeling approach, you dramatically increase the scale, reduce the cost, increase the quality with which you can find solutions. How do we build these systems? Are there any questions so far? Yeah, go for it.
And did you find any weird stuff from your data at NAC?
Did I? I'm sorry?
Did you find any like interesting data that from NAC? Like the in previous example from the OK, like if like I don't know.
Oh, did we find anything that was interesting?
Yeah.
I think the first thing that I found was interesting is that it works, which was like mind blowing. Which was basically nameless company. They had this experimental program in which they hired something like 500 people, and you know, some of them work out and some of them don't work out. So what we did is we had them play our games. And at the end of sort of this like evaluation period, the company was like, all right, Knack, we want to see how good your stuff is. Like, what's your evaluation of these people? And like we gave them our evaluation, and it turned out that like nearly all of the people who we said were good, and the people who we said were bad performed badly. So basically, what that means is that like, so for example, if they simply said, if they simply looked at our data and they're like, all the people who we said probably wouldn't work out according to their standards of what constitutes a good person, they would have saved tons and tons and tons of money by not training those people. And saying, you know, like, you know, we have this additional data point in it that we can put together with your interviews and your background, and we think you're perhaps not going to thrive in the culture that we have here. So actually, this is a really good example. So there's, I think it is Walmart that does this. Their call centers are staffed entirely by algorithms, so people are not involved in hiring decisions of these people. What they do instead is they created this this questionnaire, this computerized questionnaire, and they have you answer it, and based on how you answer this questionnaire, they decide to hire you or not. And basically, they figured out their definition of optimal employee is someone who does not possess empathy and lives close to their job. So this questionnaire is meant to whittle out, do you lack empathy, and do you live close to the job? Because basically what turned out to be the case is that their definition, which may or may not be Walmart, I don't know if it's Walmart. Please do not, I'm not liable, okay, anyway. So, they determined that what constituted a good employee was someone who would stay. So basically they're investing all of this time and money into training you, they really don't want you to leave. And so basically they figured out the two things that had the greatest correlation with you staying are, one, if you have a lot of empathy and like you're on the phone with people who are suffering, like basically people, you know, you're causing pain in people's lives. Like, yes, you paid, you know, $1,500 for like a flat screen TV, and like, I don't care if it broke, it's your problem. Or like, you know, you have to sort of be willing to endure like emotional turmoil, and be able to make it through to the end of the day and go home. And if you live really far away from your job, that's another thing which sort of heavily influences you not wanting to go there the next day. So that's a really interesting example of people using algorithms to do hiring. But that's an extreme case because an algorithm is entirely doing hiring. Are there any other questions? Yeah.
So just out of curiosity, how many, for your experiment at your company, how many dimensions did you end up extracting, and how many did you end up using at the end that really defined?
Like the features?
Yeah.
I'm not allowed to talk about the features that we extracted. Sorry, I'm sorry.
Number-wise?
I'm sorry?
Number-wise?
Better not. Maybe if you come talk to me later on, we can talk more about that. I'm a spy. Anyway, okay, so an example. So I thought what would be really cool is we could think of a simple but non-trivial example. So what we're going to do, we want to build a website that does the following. It is a personalized haiku engine. So what happens is, it's this website, people log in, they're constantly entering haikus. They're just like writing haikus and submitting them. And you log in and you're sort of presented with a list of recent haikus. And the idea is you want to present to the user sort of like, here are haikus that are tailored for you. Here are like the top 10 haikus that you will enjoy. So that's what we want to build. So by the way, if you, yes?
What's a haiku?
Are you serious? Sorry, so a haiku is a poem. It's a Japanese, it's a poem from Japanese culture. It's very short, it's 3 lines. So the rules are that each line have, the first line be 5 syllables, the next one is 7 syllables, and the last one is also 5. So it's very short, sort of it's an exercise in being concise. There are also additional requirements, like it has to be sort of seasonally related. So like if it's, and of course, seasons in Japan have different telltale signatures than in other nations. You can talk about like cherry blossoms, if cherry blossoms bloom, things like that. And people have sort of adapted that to doing the same things in English or in other cultures. So trying to think of a witty haiku, but my brain is failing. Anyway, that is a haiku. Yes. Oh, so by the way, if any of you build this, I guarantee you an interview. Okay, so first thing you got to do, you got to receive the data, right? People are coming to this, right? They're writing haikus, and you want to be able to look at the data and sort of make some sort of analysis, gain some insight about it. First thing you have to do, you have to receive it and keep it. So what are you going to do? You receive the data, you write it into a database. The problem is if you have this so-called high-quality problem of lots of people coming to your site, eventually, so that one node there, that one database, can only withstand on a commodity machine something like on the order of a couple thousand simultaneous connections. When the number starts to go beyond that, what happens is at first requests start to take a long time to get fulfilled, and then they start to drop. So in order to fix that, so if it weren't writing, if it were simply doing readings, like you're just going to a website and you wanted to read like the front page of the New York Times, does anybody know what the solution to this problem is? How do we scale reading? Replication? Can you tell me about that? What is that?
Where you take your database and you copy it to many different servers, and then you have some type of load balancing machine that will either randomly or systematically point the client to a server. That's
correct. That's exactly correct. So replication is the answer for in the case of reads. So just to reiterate what you said, if you're reading data from this database, when the number starts to become too much for this one machine to handle, what you do is you make copies of it across multiple machines, and then as requests come in, you just sort of evenly distribute them amongst the machines using a load balancer. The problem is, if you are instead doing writes instead of reads, if you make copies of it and you do the same thing, we just have copies of the machines and a request to write something comes in, that write request has to go to all of the machines in order for them to stay in sync with each other, right? So if the write just goes into one machine, now the machines are not perfect copies of each other. So what happens is that if all of the requests are going to all the machines, you have not reduced the number of requests experienced by a machine, so you have not increased scalability. So the way to make writes scalable is to do basically what I just said. The requests to write have to be distributed by machines. So some of the writes go to one of the nodes, some of them go to other nodes, some of them go to another node. And basically some nodes sort of become the owner of like a certain region of writes. And the idea is that when later you want to read that record, you have to know, well, which partition did I stick it in? So this is called partitioning or sharding. And the thing that's important is you have to think about what is the criteria by which I split on. So for example, let's think about the haiku example. People are coming in, they have an account, they're entering their haikus. What is some criteria by which you might want to split the data, which database the haiku goes in? Does anybody have any ideas?
Like number of users, like I can share by user.
What do you mean? So here's the, so I come to the site, I log in, I type in my haiku, I hit save. How do we decide which database it goes to?
Like, I mean, approximately, for example, you have like 1,000 like users. So you can like divide it first 2,000, like 2,000, yeah, 2,000. So first like 250 goes to this server. Like the second 2,000, like from 2,050 to 500 goes to the second server, and so like you split by users.
Yeah. Actually, so that's a variation of the idea of just by names, so like user ID. So like this range of user IDs, well, you get assigned to this database. This range of user IDs, you get this other database. That's pretty much what you were saying?
Yeah.
Does anyone have any other ideas? Please.
You can do by keyword, like if their haiku has a certain keyword in it.
Ah, that's
so
an
it's
interesting
like
idea.
theme or something.
That's really interesting. That is a very interesting idea. So, I have not thought of that. But the idea that the thing that we're trying to preserve is that requests should be evenly distributed as much as possible amongst the databases, right? If it's totally skewed, then you haven't really increased the scalability at all. Now one database is still receiving the bulk of the writes. So you want to have some scheme that sort of evenly distributes it. Was there?
So maybe like based on the time of day that it's made, because theoretically, like one country would be reading its own country's haikus. So you want to spread all the American ones out across all of the servers, so that like when the Americans are all asleep, then like you spread each country out like across all the servers, not just a country separated. And so when one country's asleep, the other one will have access to all of them.
Region-based partitioning.
Yeah.
Yes. So everything that I've heard so far is something that is actually used in actual systems. Yes.
How about keeping a global count of how many users are attached to each database? And at the same time, you can also factor in some sense of how far away the database is from that particular user, and do some sort of weighted average kind of thing.
Oh, sure. I see what you're saying. Yeah, absolutely, totally. So, yes, all of these are good answers. All of these. Yes, sir.
I would ask you what kind of query you want to run.
That is a good question. Well, so the issue of, yeah, so that's basically the issue of like, well, what do you want to do with this data once it is stored?
Yes.
But if we're first just thinking about the problem of how do we, in order to read it, we first have to solve the problem of we have to store it. In order to store it, we have to be able to evenly distribute it amongst the nodes that we have in order to receive writes.
Yes, but you do want to, when you're talking about distributed data, you want to plan your queries accordingly.
That's true.
You want to
But-
limit access to as few servers as possible on the read.
Why do you say that?
It's faster.
Was there another? So everything that everybody talked about is something that is actually used in order to decide how to do partitioning. So one of the issues is just as as my friend Jason was saying, it depends on what is happening with this data. So for example, let's suppose that if you split based upon just user ranges. If the nature of your data is such that maybe 10% of your users are using like 90% of the system, so like only a very small number of users are actually most of the activity, then what's going to happen is like just the database that those users are on like is going to get all of the activity, and like all of the other databases will be ignored. But what could be the case is that in another application that isn't the case. Like maybe in some sort of other application, it's totally perfectly distributed amongst the number of users. That's just sort of the way the application is built. And in that case, splitting by user ID is totally acceptable. Something that's done in practice here is you create something that's called a session ID. So basically you take parameters that everyone was talking about, you compress it into some sort of what they call a hash, which is just basically a 32-bit or 32 character long number, and then that basically becomes the key for this piece of data. And then when you want to, and the important thing is that when you want to go find that piece of data again later on, you're able to recompute that key and then go into the database and be able to retrieve it. So one thing that's really good at implementing this scheme are NoSQL databases. Can somebody tell me what that is? NoSQL database? Does anyone have any experience with this? Yes, please go ahead.
It's like a weird definition. It just means basically not a relational database like a MySQL or a Postgres database. So it can be like Cassandra, which is call of the family. It could be MongoDB, which is document, right? And then there are a few others.
That's correct. That's exactly correct. Did someone want to say something else? So yeah, that's exactly correct. It's not relational. They are often basically a key value store, which basically means you have a key and then some sort of unstructured data. In contrast to this, you have a relational database, which is you explicitly specify the schema of the data that is being represented. So the NoSQL database is really, really good at doing this, because what they often provide you is, well, you have the key by which you're entering stuff, and they let you sort stuff by that key. So they will give you an index based on that key. So you can sort of say that, like, okay, I've got this database. If I want to find this number of, if I want to find, for example, the session ID, it'll very quickly tell you, okay, this is precisely where it is. You go here, and then you find it. The problem with this is that it is very hard to read data out of this. Can anybody tell me why that's true? Yes.
Well, if it's like a SQL database, then you can like search for an item based on like one data value or something. But if it's based on like a hash map or something, then you need to know the key in order to read a value.
That's perfect. That's exactly correct. So basically, that's the reason. So for example, so we talked about partitioning based upon this one key, session value, or user ID, or region, or any of the values that were proposed. And that's the thing by which you propose to do the split. The problem is, when you want to sort based on another attribute, so for example, let's suppose that you want to answer this query. Give me all of the Haiku sessions that occur between October 10th and February 1st. How would you solve this problem? Basically, the way that you have to do this is this is only sorted according to the session ID, or user ID, or whatever. In order to examine it according to some other attribute, what you have to do is collect all of the records from each of the partitions, assemble them in a list, and then look at them all. Very, very inefficient. Which is exactly the problem that an index solves and a relational index. So this is an interesting conundrum. So basically what this means is that the place that is really good for writing lots of data is really not so good at reading data. And the place that's good for reading data is not so good at writing tons of data. So a solution is basically you leave it in the sharded location while it's active, while people are doing tons of write activity. And when people are done, you move that to a relational database where people can issue complex queries on a bunch of attributes. Okay, you got the data. You're able to read it. Now we want to learn some stuff about it. Okay, so learning algorithms and applying them to data, there is some amount of art and trickery that is involved in the process. So in this case, the problem of recommending a list of haikus to people, the category of this problem is called a recommendation system. So that's sort of the buzzword to go look at. Some approaches to this problem are something called collaborative filtering. Another thing that I want to look at. And I will send a list of resources for people who are interested in finding out more stuff. So the approach that we're going to examine right now, just at a very high level, something that we talked about before, which is called co-clustering, which is basically what Netflix does in order to do their recommendation system. So co-clustering in general is, okay, let's suppose you've got this thing that you're sampling about the universe X. So like, for example, words. You're just looking at like, you're just looking at words that you examine that just appear in your face. Like you go to a web page, you're reading books, you're looking at some academic paper that you printed the other day. All of these things are filled with words and they're just sort of being sampled from your face. And you can sort of count the frequency with which you look at these words. And so you can sort of form these things like, okay, what's the probability that I see the word the? What's the probability that I see the word defenestrate? But let's suppose that this is the input to some sort of system. can sort of observe something as a result of this. So for example, let's suppose you enter this word into, you know, like these are words that like you say to a person, like a conversation partner. You can sort of observe what did they say in response. So now you get these sort of pairs of things that you're observing, X and Y. And now you can sort of talk about, well, what's the frequency with which I observe the pair X and Y happening together? And you can talk about, well, what's the probability of X and Y happening? So a good example is, that they talk about in the paper, is X is words and Y is documents in which those words appear. So the idea is that if you're just looking at words, and you're just counting the number of times that X appears, you can talk about sort of the probability that a word's going to appear. But if I tell you that, hey, you're looking at a paper about aeronautical engineering, that dramatically changes the probability that you're going to see a sort of word, right? So if I tell you you're going to look at a word about aeronautical engineering, you're probably not going to be reading a Hans Christian Andersen story, right? You're going to, it dramatically will increase the probability that you'll hear words like measure, or calculate, or differential equation, or things like that. So the idea is that if X and Y are somewhat correlated, you can learn about stuff that's in X from stuff that's in Y, and then the other way around. So in our case, X is going to be some features about haikus. Y is going to be the haikus themselves. So this is part of the part that is the black magic part, and takes some trial and error. There's thinking about, well, what are the features? What are we going to be looking at about these haikus? What are the two things that we're going to be correlating? Should we correlate the features in the haikus? Should we correlate some other sort of feature? And like instead of the haiku, we could correlate an action that the user does, like that they forward it to a person, something like that. So these are sort of things that have to sort of be experimented with there to see what sort of success results. But let's consider this case. This is the space of all haiku features. So a feature might be, for example, the presence of the word cherry blossom, or the phrase cherry blossom. Like if that appears, that counts as a feature. So you're sort of saying like appears 1, not appears 0. This is the space of all haikus that are on your site. So basically here's every haiku. Co-clustering, what it does is identifies, it says that, oh, okay, whenever I see this haiku, or it's in this box, it tends to be appear at the same time as features that are over here. And it sort of finds out these groups of things that tend to appear at the same time. That like, oh, okay, this sort of like list of features, this sort of group here, they can be grouped with this group over here. And sort of, I'm talking very informally, the sort of technical definition is, if I told you the identity of a haiku here, if it sort of maximally skews the probability, like it gives you the maximum amount of confidence about what sort of features you're going to have, that is, it gives you the most amount of information, and information theory speak, about the nature of the features that you have over here, then it belongs in that group. And same thing is a symmetrical relationship. So it goes the other way around as well. So if you know about features, then you can infer something about what haiku you're looking at. And so what you can do is, if someone on your site is looking at a haiku and they say, I like this haiku, what you can do is you can look at the cluster that it is in. You can say, ah, well, it's in this same cluster. That haiku is like another haiku in this cluster. I will recommend one of those other haikus to you. So this is just brief skimming the surface of this problem with co-clustering. There are tons of issues to solve, which is the biggest problem, it's basically the biggest machine learning problem. Is basically what should I be paying attention to? What is important? What is a significant thing that I should be looking at that has that like can tell me something interesting about the problem? Basically, what is your feature space? So, for example, in the case of haikus, or really anything involving words, people often use something called n-grams. Does anybody know what an n-gram is? So an n-gram is basically If you have a piece of text, you want to do a classification, you can just look at words by themselves. Or you can look at the word in the context in which it appears. For example, the word and the word to the left and the word to the right. So that can be a feature. So for example, you could say like, well, I've got cherry blossom, but on the left does the word a appear, and also on the right does the word query appear. So like a cherry blossom query. When those three things happen together, that 3-gram, we can sort of say like that it appearing or not appearing counts as a feature, and that's something that you can consider examining in your machine learning algorithm. How do we initialize the system, right? When you turn the system on, like you've got nothing, you've got no data, you have no counts of anything. So how do you start it up? Turns out a good approach to doing this, which is weird, is you just sort of select random settings, and you just sort of let the system update as people use it. And how do we update clusters as data comes in? So basically, what that means is like if we're sort of updating these clusters as people like and dislike stuff, does that mean like the recommendation's going to change just like all the time, like every time that they visit the site, like they're going to get a whole new set of recommendations, or should we sort of dial it back so that the recommendations that they receive, they change slowly, they change like maybe week to week or month to month, so that it's not a jarring experience, they sort of have some sort of sense of sameness. So that's really all I wanted to talk about. Basically, just give you a flavor of what's out there as far as what is the problem with big data and machine learning. Why is it a big deal? What are some things that are involved in building these systems? If any of this seems interesting to you, like you want to know more about this, you want to sort of get your hands dirty with this, please come and talk to me. Or better yet, come and send me your resume. We are hiring. And you can come and work with me and the people that I work with to solve these problems, all of which are unsolved and we are figuring out. You can reach me at my company address, which is don@knack.it, or on Twitter at Don Dini. Thanks very much. Are there any other questions? Yes, sir.
What was the idea? What are you going to do with the Haiku? I mean, like, what was the initial plan to do with the Haiku? To cluster them or what?
I'm sorry, I didn't get that.
What was your basic idea to do with the haikus? What are you gonna do with it? Are you gonna cluster them or what?
Oh, with haikus?
Yeah, or with haikus.
Oh, so the idea. Well, so recall the user experience that you're trying to create is that you come to the site and you see haikus that are tailored for you. The idea is that, like, similarly, like when you go to Netflix and it sort of says like, here's the top 10 for you.
Recommendation, yeah.
Exactly. Recommending haikus.
And what's like algorithm, like machine learning algorithm, you're gonna run for this haiku?
So the algorithm. So there are many algorithms which you might use. The one that we talked about today is something called co-clustering, which is what is used at Netflix to solve this problem. But other popular approaches are things like collaborative filtering or modeling-based approaches. So things like logistic regression or linear regression.
And how could this algorithm, like, what is the percentage given? What?
I just thought of this problem like yesterday. So like I haven't built the system, so I don't. But like probably what would happen is if you went and you did this and you used sort of an n-gram approach and you did co-clustering, that would probably be enough to get you sort of like to 80% or so, where 80% of the time someone came to your site and they would sort of say like, wow, that actually is something that I care about. That is really cool. Like I really enjoyed this haiku. And that's sort of going from 80% to like 95% is hard and requires time and effort. Sorry, yes please.
So why don't you use LDAs because there are too many topics?
Why don't I do what I'm?
Latent relationship allocation. LDA.
Oh, LDA? I'm not familiar with that particular algorithm.
It's where you model each of the topics with the relationship allocation distribution, and then you maximize it. You find the parameters using the EM algorithm, and then you can get a set of topics.
I see.
And then each word that you get is allocated to that topic.
Oh, I see what you're saying. Yes. I mean, yeah. I mean, so there. Co-clustering is just an example that example approach that I wanted to talk about just for the sake of illustration. There are many. I mean, there are one of a host of algorithms that you could use. Actually, what's really interesting is someone did the study in the, I think it was the late '90s or early 2000s. I forget the names of the authors. Anyway, did this study where they compared a bunch of machine learning algorithms, such as support vector machines, neural networks, logistic regression, clustering, like all sorts of, like they just like put them all on a graph and they sort of said like, okay, how, like let's suppose that you have, let's consider a problem for which you have like basically an infinite amount of data. So like, for example, like image recognition. So like, you know, you could go on the internet and just like download basically infinity many images. And let's consider the problem of like classifying this. So for example, like is there a cat in this image or is there not a cat? What they found is that all of these algorithms basically end up converging to doing equally well in the limit of as you keep feeding it data. So it sort of has led to people saying this phrase, which you may have heard before, that it's not the algorithm that you use, it is the amount of data that you have, which is the significant thing. Which is often true if you are in a situation in which you have lots and lots and lots of data. Yes?
But that also depends on the amount of time you have and the amount of data you're willing to use, because some algorithms would be more efficient and they give you more better results much sooner.
This is true. So it's especially important if you don't have a lot of data. So for example, in the case that we faced at my company, and we were looking at these people that were, it was like a group of like 500 people or so. This is not a large, it's not like looking at like cat images, right? It's a lot of data, but it's not like tens of millions of points of data. And so that entails different approaches. Are there any other questions?
So, I mean, Netflix used this algorithm called clustering, right?
Mm-hmm.
So, I mean, the main thing that everyone has access to this co-clustering algorithm, right?
Mm-hmm.
They can implement it. But, like, the main thing that Netflix would,
They leave out a lot of details in the paper. It's very general.
Okay, so it's, I mean, would you say that the research that the other team that Netflix kind of hired or was for the competition, so the research that they did, like, was it basically the features that you look at and then apply this algorithm?
So there were, let's see, so the team that ended up winning the competition was, I believe, was not a psychology inspired. So that team that article was written for, the psychologist about the Trump, the data people, he ended up losing, and another group of people ended up winning, and some of their code ended up being incorporated in the actual algorithm. But the thing is this co-clustering algorithm just completely obliterated it, and more importantly, that algorithm didn't scale to the size in which they were interested in, and it was an offline. So it didn't. So basically, you had to sort of like compute a bunch of results, and then you're done. Like you sort of had to use that sort of ongoing, and then periodically perform a recalculation. Yes, sir. Do you have a question? Are there any other questions?
So other than like recommendations, what are some other practical applications where people can use like machine learning? Like what kind of other data can you extract from that system?
Sure. Well, all of it is sort of going to be some form of classification, right? So not necessarily like here are things that you would like or like so in recommendation system, it's sort of the problem is sort of like will you like this or will you not like this? Is sort of the classification. But there are other things like, for example, like I talked about real estate prices, where the thing you were trying to map to, right, is dollars, basically dollars per square foot. And sort of you sort of feed it like a bunch of features, and it tells you like, okay, here's how much money you can expect this place to sell for. Yes, sir.
So if you actually start modeling, with all this data and this type of algorithm, you can start modeling demand, dealing with your real estate example, right? You can say that people like X amount of X, Y, and Z features. And once you've consumed that data, now you can start modeling, saying, okay, based on the open market and housing with those features, we can actually extrapolate mortgage costs, mortgage rates, and what will the banks charge to have a home in Malibu.
Mhm.
right? And charge more or less, I mean, based on the, that's kind of a practical application of what this modeling, this data can do, right?
Yep, and people do that very thing that you're describing. A really cool example actually was so in Los Angeles in the I think it was the 80s, there was a really terrible smog problem. I think before then as well. It was so bad that they would advise people not to go exercise outside. They would have like smog advisories where like they would say like you shouldn't send your kid outside to school today. You would keep them inside. And what would happen is that they would be issuing these advisories like basically the day of. So like when they're sort of ineffective. So like the morning of, like they'd be like, oh, okay, today is going to be a really smoggy day. You shouldn't go outside. But people were they had sort of prepared themselves to go. They sort of hadn't set up their life to like not go. So they had to go anyway. So the thing that would be really useful, that would sort of help people to be healthy, was if they knew like 24 hours ahead of time, or 48 hours ahead of time, if it was going to be a smog advisory that day, so that they could then go and inform people. So they came to data scientists and they sort of said, can you come up with some way where you can look at conditions today and you can predict 48 hours from today, will there be a smog advisory? I think they had some success, but they weren't super successful doing this. Because I guess it was really hard to run. But that's another example of something that people tackle with the machine learning data approach. Another really fantastic example, actually, is audio recognition on Android. So basically, the entire audio, the voice recognition system on Android devices is entirely a big data triumph. That's it. That is done. Actually, they talked about. There's a lecture by the guy who's the director of the Stanford AI Lab, Andrew Ng. He talks about basically how Google did this in this like amazing lecture about. Actually, I can send a link to that, and then I'll send it to Brian, and then Brian can send it to everybody. But that is basically that's another huge triumph of a data approach. Yeah, thanks very much. If you want to talk about anything in greater detail, please feel free to come talk to me. Or send me an email.